I never pushed so many deadlines in the last couple of weeks. It's like 2 homeworks due this week and then there is a final exam. Crazy hours.
We also had the second midterm.
Oh, that was also due this. Yeah, it's 4 submissions in the last 2 weeks. I don't try to do that, but it just happens.
When do we get the final exam?
Probably today itself, yeah. I was waiting for others. I was planning to do optical theorem in the final exam. But then I'm seeing that it is building on, like it's getting long. And I don't introduce a little, some new concepts. So I'm thinking that, okay, I could drop that idea. Might be simpler. Probably a problem from the last final exam. I'll take a problem and put it. So, and that's another comment that there are so many things due. I don't want to make the final exam again long. I'm planning to make it simple, some smaller.
Thanks.
At the price. Yeah, thanks, but you also miss out on it. That's a price, right? I mean, when you do it, you get to know the topic.
Can you still post the quantum optics?
Quantum optics?
Yeah, that board one against the final.
Oh, optical theorem, you mean?
I don't, yeah.
Yeah, I have the notes for it, so it's all typed in everything, but when I'm looking at it, it's really going to go long. So how about this? I'll put it as a notes. Yeah, how about this? I will have a 4th question where you just have to look into the notes. You don't even have to write down anything, you just look at the notes. Reasonable, yeah, good point. So that way, I gave you a chance to at least think about the topic. So, yeah, that's a good thought. Yeah.
It will be graded.
Huh?
It will be graded.
About looking into it?
You can.
Yeah, if you don't look into it, I'll not give you the points. So you have to look at it, look, but you don't have to write anything. You just have to say that I looked into it. Right? Reasonable?
Yeah.
So I cannot test you on how you looked into it, right? Whether your eyes were closed or open when you were looking at it. Good point. Yeah. There is mass. Give it a minute. Yeah, so there will be 2 questions. One will be from the last final exam, basically extending whatever I here will do it for 1 point particle. You will do it for a ring or a disk. I think it's a disk that I gave out. So scattering of a disk of a material in the shape of a disk. And that should be simpler, I would say. The next problem will be optical theorem, just looking into the notes. And I know one problem that I'm going to give, it's going to be on dimension analysis and scattering. Some equation I'll pick from the scattering theory and do the dimension analysis for it. Maybe that's the only question that my time I might do, but maybe I'll think of one more problem.
This for the take home part or in class?
In class. Okay. Take home is going to be 2. One is looking into the notes. The second is from the last year final. So I just have to cut and paste and put it here. And first and second question is very simple. The second question is on dimensional analysis. First question I haven't thought about yet.
And how about the in class part?
That's what I mean. Okay.
The
Confusion. Okay, I'll write it down.
okay. Take home part.
Let me write it down. Okay. So submissions are all, I'm not even writing the submissions. It's all understood that this week we have submissions, right? But submitted. And I did great. I did great in the sense for attempting, I graded it. and returned it back to you guys, but mostly just for attempting. I was thinking of creating the electric field lines, but I think Aryan did not submit it, and I thought he was talking about submitting, and I think someone else did not submit the electric field lines. I thought was not bad. So I did, basically ignored it. Some of you guys work hard on it, so sorry about that. Okay. So, final exam is due, like, will be uploaded today. Due 8 AM, right? 8 AM Friday, May. Hmm? Yeah. Okay, and so, yeah, so there will be 4 questions in the final. The first one will be in class. I don't know, anywhere in the semester. Second one is on diamond, so again in class. So this one I don't know where it is because I don't know yet. Second one is also in class. This is from dimensional analysis. In the later part, in the scattering. There are plenty of equations in scattering where dimensional analysis requires a little care. If you just take current and assume that it's current, it doesn't go through with it's in the Fourier space, so you have to be careful. So something along that line. And third one is from scattering. So this is take home. This is take home. And it will be scattering of dust. And fourth one is so this is also for mass, take home. And how do you say this? Then you have to look into the picture. Look. Yeah, so it has to be late. Still your questions?
What's that?
No.
No.
Okay. So maths you came late. First of all, yeah, I should return your calls. Okay. We were saying everything is due this week, whatever is remaining, try to make it due. And is it correct that some of the lectures have the solutions to the homework that I'm going through? Is that correct? Some of the lectures, so I go through that. So
I think homework 13 did,
okay,
or was that homework 12? One or the other. I forgot
Okay.
which one.
but you guys are communicating between each other, right?
Yeah.
Yeah, this is that, yeah, so that's good. Okay.
Yep.
Okay, so primarily for maths because he's from a different department. So share with him also, maybe he's taking the initiative. I don't know what's going on in your group. Yeah, okay, so that's good. So the final exam I was telling is we'll have 4 problems. First two will be in class, they'll be tiny, like can be done in 5-10 minutes sort of. I don't know which topic it will cover, so it could be anything. Maybe relativity, we spent a lot of time on relativity. Take something from relativity. Second one is in class, it's on dimensional analysis. There are a lot of equations where we go into the Fourier space. And whenever you go into the Fourier space, like when you say current, you think that it is charged per unit time, but it's not charged per unit time in the Fourier space, right? Because there's more things that come up. So that one, third one is scattering of a disk. This is exactly from the final exam from the last year. And that should be, that went well last semester, so at least you know what it is going to be. And I'll reveal it today. Today I'll upload the final, and the fourth one is take home, but this is what I was planning to make. But along the line, I decided not to give it because it seems to be too long. But then Ryan suggested that it will be good to at least see what I was thinking of putting in so that you don't miss out on the topic. So the fourth question, you have to look into those notes. Okay, just
You
look
have
at
to read the question.
Read it but not do it.
no submission needed, okay? So just, yeah, just look into it.
Look and learn.
At least click on it. And see what the color of the paper is, color of the background.
It's not even white.
Could probably, maybe it can be right, but.
I'm surprised if it's red. I've never seen a red exam.
Exactly.
Never seen a red. I've seen other colors.
Red is how would you mark off?
Today, I was talking to, like, I finished my other lecture. And he was saying he's colorblind and how it works out. Because I think I am blind in my left eye, so I was talking about ray optics. And then as an application, you say that corrective glasses.
Oh, yeah.
So, and then I was saying that when you fix your eyes, like eyes has two, in very simplistic terms, one is a lens and one is a retina. When it comes to the lens, it can be fixed very well. It's very successful surgery. Anything related to the lens, they just take it out and put it back. Very quick. It's almost outpatient. You don't even have to get admitted. Come do it and they go, and extremely successful. But when it comes to retina, it's zero success. Like they won't even touch it because it is nerve endings. And I have retinal, my retina is torn at the back. So even in the front, this white thing that you see is basically the lens getting opaque. That's why it's reflecting and it's white. But at the back, this can be fixed. White can be fixed. Cosmetic things that can be fixed. But I say, who can? So at the back, retina is completely torn. So I was telling them about how you fix corrective glasses, like how a convex lens and concave lens, and that led to the conversation that, oh, what do you miss out when you don't have one eye? What do you miss out, by the way, if you don't have one eye? Do you miss out on anything other than the range? Of course, you don't see half of it. You only have a small range. What else do you miss out on? Nothing else? No, there is something important. No,
As you see, 50% of everything.
that's a range. No, that's the simpler thing. There's a significant thing with two eyes. Yeah.
Isn't it parallax?
Yeah, what is that? Stereoscopic vision. You see depth,
Yeah.
like you can really measure depth. Basically, the angle that we see it, like two rays coming in, our brain is smart enough to measure that angle or extrapolate it, and you can measure that angle. And based on that angle, you can measure depth. Like our brain can calculate depth. So close your eyes, and next time when you do something, the best I have noticed is when you pour water on a dinner table,
Oh, yeah.
try
I see
to
it.
pour water into a glass with one eye closed. I mess up all the time because I don't have depth. Yeah, so like when I'm driving, when you go to an ATM, you have to make sure that your rear view mirror doesn't bump into the ATM.
Yeah.
You want to go very
The
close.
drive through.
Yeah, I'm gonna drive through ATM, and that's requires depth. And I don't have it, so I mess up.
Sometimes I miss it.
So it's not much different. Makes sense.
You're not missing much.
I should say that even those many people who have two eyes, if the power in one of the eyes is not the same as the other eye, our brain tends to use only one of them. So then you lose depth also. I'm not saying you have that, but you have like not everyone is used to using two eyes. It's very easy not to use the second eye. Like it's like teeth, right? You like to use both sides of your.
It's like the good eye can see more brighter than the other.
Correct. So then you say like forget the bad eye. So anyway, got a lot of stuff there, and one eye can be used to see depth. Like, for example, any motion in this direction, I can sense. Like, for example, you're playing baseball, ball is coming towards you. You know, if I think it is the muscles, like I think we train our eye that, oh, the muscles, there is some distance is coming closer. So something your eyes does so that you can sense the depth when there is motion in this direction. But when there is motion in the vertical direction, I cannot. Like, for example, badminton, usually the shuttle is coming from the top, like it is, the motion is mostly here, then I have problems. I'll be the shuttle here, I'll be waving it somewhere there. But baseball, cricket, that's easier. You do a reasonable job. Of course, you will miss out on it, but it's okay. Anyway,
So is there a solution for this? Yeah.
I don't think so,
Like some kind
unless you have the second eye. To fix the second eye.
of corrective glass?
For me, corrective glass will not work because it's not the lens, it's the retina. So retina is almost no, yeah, very hard, basically nerves, anything with nerves, we are way behind, we don't even touch it. Even spinal cord, back and all, you try not to touch it. We are good at replacing the whole thing, take the whole thing, put it back, and if it grows back, then this.
So no one ever has done this surgery?
Of retina, I think very rarely, it is done for very old people, but pretty much, no, I mean, yeah, the simple answer is no. They do this, the following, again, it has been done on me. So my right eye is now very good. Right, and it is very important because anything happens to the right eye, I get blind, right? So now retinal tears means things getting, the retina is basically a skin and it can get a tear. And like a cloth, if you have a tear, it can expand on. So you don't want any tears to start showing up. So sometimes in every eye, there are tears on the retina, like basically a hole in the retina. So you want to fix it. So what do you do when there is a tear in the plug? Sew it up, right? So around it so that it doesn't spread up. They do the same thing for retina. What do? They take a laser and they just burn it around, all around. That's all they do. They take it, burn it around. So I have done this about 2 times on my right eye, where there are small tears that show up. So they just take burn it. Just burn it.
What causes them those tears?
Huh? What causes it? I'm told, again, simplistically speaking, this is a retina is basically a skin stuck on another skin. This is the nerve endings from the brain. Very simplistically speaking, this is what it is. Now, let us say I fall, right? I just jump into my bed, let's say, and my head comes and hits the pillow very hard. So there is a pressure, like this has got a strain, and in a small region, it can just come off the other skin. That's it. And there is now an air bubble there. So when you say a tear, that's basically an air bubble inside it. And that air bubble starts moving around. And that gets bigger and bigger. So one of the things that led to this left eye, I have had 2 injuries, is that I basically fell onto a cabinet. And then basically the tear, already I was blind, but then the whole retina just fell into the eye because it was very weak, because it was not being used. So did I answer it? Very simplistic. It's not a physics problem, but yeah, very simple. That's what.
I mean, optics have to do
Yeah, sure. Yeah.
Also electromagnetic.
Yeah, light, right? Light. Yeah. Yeah, it's amazing. Ray optics, like whatever we do here, we have not even started optics, but we have to use these equations to get the reflection coefficient. But in the introductory physics course, I somehow reached Maxwell's equations or 4 equations. And then you immediately see that these are oscillations. This is a wave equation. And the whole wave equation is approximated to a ray. Right, and that's ray optics. So whatever we are doing here in the extreme scenario is just one line. And once you have a line, then you do geometry of a line and geometry of a circle and a line, and you can do various things. In fact, you can predict a lot. You can build a microscope and a telescope using ray optics. Okay, after 20 minutes discussion on red and on lenses, let's see what can you. I got finished today, right? I cannot leave anything hanging. So what we have is we want electromagnetic scattering. So let's begin with Maxwell's equation, right? Maxwell's equation, at least 2 of them, is the cross electric field. And let's write it in the partly in Fourier space. The time is in the frequency domain, and that's equal to I omega B or omega. That's your Faraday's equation, Faraday's law. If you want it, it should be time derivative, but time derivative gets replaced with minus I omega in as well as practically speaking, that is what is happening. One more equation, L cross H, or omega is equal to minus I omega B or omega. That should be J also there, plus J, but you're saying you're in a region where there is no electric currents and no charges, so that's equal to 0. Clearly, this also implies we need 4 equations, but if there are no charges and currents, you can take a divergence here, and it implies that delta B is equal to 0. And this also implies that delta D is equal to 0. Like no charges and no currents. So that's true. We are also saying B is equal to mu naught times H. So there is no magnetic material. But when it comes to electric material, we want to have electric material. So there is electric responses, but we say it is isotropic. There is epsilon, but it is isotropic. In general, it's a dyadic, right? So I'm saying it is isotropic. That's a simplification I would make. Okay, so that's any questions? And epsilon, we will also have pi will be epsilon over epsilon naught minus 1, right? Since it is isotropic, no dyadic. Needed. Okay. We mixed up these equations and we got a differential equation associated with this last time. And we said that's equal to minus 1 del square plus omega square over c square. The electric field or omega is equal to omega square over c square chi. It is isotropic omega times electric field. whenever, so that's a homogeneous. Inhomogeneous equation where the inhomogeneity is completely coming from the source. This is what our source is, right? We are saying that there is a material electromagnetic wave coming in and going off. So the problem is like, so there is a chi here. That's a material and it is confined to a region. You will use delta functions and step functions to define your chi. And electromagnetic wave comes in, which will be the incident, let's say E incident R of omega, and it will come and induce electric field or polarization. It will induce polarizations in that. And once those polarizations are oscillating, if you have a dipole that is oscillating, then that will radiate. Our simple conclusion from earlier was that any charge that accelerates radiates. So if there is a dipole that accelerates, and the positive and negative charge that accelerate, so that will radiate, and that's the radiation we have. So the same, this is a two-step process. So this is scattered, the electric field scattered. And once I know this, the square of that is basically my scattered intensity. So we will basically calculate the electric field, and the understanding is that the square of that is the scattering amplitude. One clear. So that's a picture we want to have. So this is the source. If not for this, there's only an incident, right? If I switch this off, then that's my free case where there is no scattering. Then I'll put this in, and what is the contribution coming in from that? And that's the idea of a Green's function. So if I have a point object, what it is, so build a Green's function, or this time it's a Green's dyadic. So I have a source at R prime, a point source at R prime. So this is your R prime. If you have a point source, what is the scattering? And the point source, I would say, is delta R and R prime. But this is a dyadic, so it has to be a dyadic on the right side also. So I put a 1 there. So it's not a normal source, it's a dyadic source because just to match the left hand side. And in the last class, we had inverted this to omega square over c square. I will put it back there. So there's also an omega square over c square. It should be on the left hand side, but I brought it to the right side. That's the definition of your Green's function, and this shows up in your homework also. I think homework 14 is mostly related to that, and you should be able to, whatever I do today, it should help you with your homework. Yes, question.
Then we R minus R. R minus R.
Oh, here, this one R comma R prime.
Is it
Yes. Huh?
Is it okay to write?
Yes. So it turns out that the free Green's function is always R minus R. In fact, it's not even R minus R prime. It is a magnitude of R minus R prime that shows up.
Okay, so can we like interpret as like in a comma also? R comma R dash, because it is.
Yes, either way, yeah. So the way you can say is that there is f of xy. So there is a function which is f of xy. This is always of the form f of x minus y. Here I have given you more information on this. This is a function of two variables, but this is a very general function. This is a very special function. Oh, this got moved. So this got moved. Did I
Yeah.
answer that? Yeah, okay.
It's in the homework, you homework 14, you have it where there's a comma and
Sometimes it is comma and sometimes it's
Yeah.
not. Here is how it is. Okay, when is it a comma or not a comma? Like if there are only two objects in space, like there is a source R prime and there is an R. Right. there's nothing else in the system, it cannot depend on anything else, right? Then it has to depend on this quantity, which is R minus R prime. Okay, that's a Green's function, but now sometimes, which is often done, the next step would be that, what if I'm doing a scattering when there is a metal in, and so there is a metal here, surface, and there is a scattering of an object which is at R prime. So again, you're talking about, say, there is some light coming in, going there, and that's your observation point R. Now notice this depends on how far you're from the metal, right? Then this distance is also expected to play a role.
Okay.
Then it will be R minus R comma R prime. So then it is not necessary that it will be R minus R. A third object pointing, even a point object, if it is going to affect your system, then there are more choices. Otherwise, if there's just you and one observer and the source, there's nothing else the world can depend on. In a sense, then it's just R. Did that
Yeah.
clarify? Did I clarify that enough?
Yeah.
Here, we haven't done this boundary effects at all. In the first semester, we do that boundary effects, right? If you're close to a conductor, what does the charge look like? There it is R comma R prime, because the boundary is going to affect it. But here, we're not doing it. One can, like when you do reflection and refraction, you do that. Like if you had to derive Snell's law, that's what you would do, then that is R comma. Okay. But yeah, so yeah, it's just the tendency there that sometimes that I think about. Okay, so let's do one thing immediately. If this is true, we can tell something about the divergence of this Green's dyadic. Operate this by a gradient operator from the left, and you will notice that this becomes del square. This is the Laplacian, and that is a gradient operator remaining. The second one, the gradient operator with 1 is the gradient operator itself.
Is divergence or gradient?
I'm using the gradient operator, but I learned something about the divergence. So currently, I'm just operating by a gradient operator from the left. Right, gradient operator dotted with this, that's a dot. Oh, maybe that's what you mean.
Yes, divergence.
Yeah, then it's gradient operator, then it's dotted, then it's divergence. Yeah, it's divergent in a sense. Usually this with the field, electric field that you do. Yeah, so it's a divergence. Sorry, yeah. Okay. So I'm taking a dot and a gradient operator, so it's basically divergence. Yeah, and del square. And here, this is again the gradient operator. That's because 1 there is a dot product, so that becomes the minus omega square c square. Now it's a divergence of this dyadic, right? Gamma naught. Oh, there's a gamma naught here. Gamma naught here. Notice, be careful. This is a dot here, right? So there's a dot in here, there's a dot in there, right? But these two cancel out. That's a basic idea. This dot is acting on the dyadic, and this is equal to omega square over c square, the gradient operator acting on delta function. And this is the reason why I was not wanting to say that it's actually a divergence, because it's basically effectively a gradient operator, but here the dot product associated. Yes.
The second term, the dot product, not between delta square.
The delta square is a scalar, so it comes out. Like this is commuting with this operator, right? Two derivatives, it can come out. This dot product is between this vector and this
Okay.
one of the vectors with that adding. Okay, because derivatives are commuting, they can come out. So this cancels this. And omega squared cancels, and you learn that the divergence of the first component of the Green's dyadic or prime omega is equal to minus of this is like your Gauss's law, right? Gauss's law says that divergence of the electric field is a charge, but now notice this is not a charge, this is the derivative of a delta function, right? So it is slightly different from what you have. Whenever you, by the way, where does it show up? If I were to say that, maybe, yeah, this might be good. So let's say charge Q times divergence of a delta function. Let me put a minus sign also. Let's say that's rho. I don't want to say anything about what does this mean in terms of charge and like physically, what would that mean? Charge times a
Charge.
charge, no, not
A point charge?
point charge, close, but something point. This is the charge density for a point dipole. Right, if you have a positive charge Q and a negative charge Q separated by a distance A, in the limit A tends to 0, right? Then you make it a point dipole. Right? And when it is a point dipole, you're basically, remember your f of x plus a minus of f of x. If I divide that by a, what is this equal to? In the limit a tends to 0?
Derivative of.
Derivative of a function, then the limit a tends to 0 is equal to f by dx times a. So derivative times a, that's effectively what we are saying. This is basically a point dipole. So when I say derivative of a delta function is a source of something, that means it is point dipoles. Polarization, remember, only when electric field comes and polarizes this, there will be a source for electromagnetic radiation. Right? All polarizations are going to be sources of electromagnetic radiation. So that's a learning experience. So let's use that further to process this. Rewrite this equation. Again, this is not part of your homework. These are the steps you need to put in your homework. Let's go back to this equation. I have minus of del square plus omega square over c square. 1 times gamma is just the dyadic itself. And on the right side, I have omega square over c square times 1. And if you allow me, I'm just going to write del cube, not write the argument for the delta function. Right, that's fine. This term. So the first term, I'm going to rewrite it on the left hand side. So that's minus 2 gradient operators acting as a divergence on.
Here for the right hand side, can you say del dot 1 is the gradient?
Yes, so del dotted, so this dotted with 1 is equal to any vector A dotted with 1 is the vector itself. Like there are 2 indices here. It's changing an index basically. it is contracting with the first index on the second index of values. So this is the second index. Is that clear? Okay, so it should be clear. Good vision. But now I can replace this using what we learned just now. So this is equal to omega square over c square 1 minus of delta plus delta and of delta function. That's the same as an operator. I will write this as omega square over c square 1 times the delta function. This time writing it explicitly. Okay. Yes.
So in the left hand side, the direct notation comes to only a vector notation of the.
Yeah, only on this. That's oh, this is sorry. This one. Is that the confusion? Yeah, it is a dyadic. Sorry.
It happens another place. That's why I thought maybe it's.
No. This was the dyadic. So now the idea is that now I've isolated, I've made the differential operator a scalar. And a scalar differential operator I know how to work with. Right.
And
So
it's
that's
just be a dyadic there too.
Yeah.
oh yeah, I've been yeah.
That's why I thought maybe.
No, I'm bad. Yeah, I'm trying to hurry here. Yeah, sorry. Yeah, since you guys are new for this, I couldn't be making this silly errors here. Okay, good. Whenever I have a scalar as my differential operator, I already know the solution to this, right? This is our scalar Green's function, right? This is your R prime. Again, this should be R minus R prime, but R comma R prime doesn't hurt it. This solution we know. This is a point charge, but this time with dynamics. If omega was equal to 0, that's scalar. Sorry, that's static. The moment I put in omega, that's a wave equation. So it's a dynamics, but we know the solution for this. This is equal to R. It is almost statics, 4 pi R minus R prime. That's your static. But the dynamics is coming from the exponential. That is a frequency dependent I omega over C R minus R prime. So that is an oscillatory exponential component to. If I know the Green's function, I immediately can solve this, pretending that this whole thing is a source. If I know a Green's differential equation, and if I know the Green's function associated with it, I can solve for it, pretend the right hand side is a source. So this is now a whole thing is a source. And that's my Green's function. So what is gamma naught R comma R prime is equal to integrate d cube R prime Green's function, like superposition principle, right? This is what superposition principle is. R prime omega, and then the source, right? Wherever charges are there, but now the source is having a dyadic structure to it. But this is all to be replaced with primes now, right? Oh, prime, this is prime plus omega square over c square, and this is prime. Let me say double prime, right? Prime, I already used it here. That's a free thing. That's double prime. Double prime is double prime, and 1. There's the function of R double prime minus R prime. There are two. There's a source and an observer already, but I'm summing over what are contributing to those source and observers. So there is a third parameter that is scanning it, so it's R double prime. Is that clear? Usually we have a function of R here, but now this is R comma R prime, so I had to use the third variable. Okay.
So you are comparing the two equations?
Yeah, I'm comparing the two. Okay, so the idea here is if I have, let's say, d square by dz square plus k square, f of z is equal to h of z. Right? Suppose that's your equation minus d square by dz square. Minus is not important, it's just my notation. So this is, let's say now you do Green's function z comma z prime is equal to delta of z minus z prime. This was what you were looking for. Instead, you go and do this. But the idea is that if you do this, that's a point charge. Then I just have to add up the contribution from all the charges. How do I add up all this contribution? F of z is equal to add up all the contribution from all the charges z prime. I'm going to add up, right? H of z prime. So this is each z comma z prime, h of z prime. Is that clear? Right. So contribution from one, contribution from for each z prime, there is a contribution. Right? Add up all that and you get the complete solution. That's a philosophy of Green's function, or that's a crux of that's the idea of Green's function, if you want. Right? That's the inhomogeneous differential equation you want to solve for. You solve for the Green's function, then use superposition principle, or basically add up all point charges to get the full contribution.
Was the gamma not supposed to be dyadic again?
Yes. Okay. Yeah. And this is. Okay. Thanks.
Just want to make.
Yeah. Good. Good. This is the simple idea, but the only difference now is that I have a dyadic in place of a simple function f. And the dyadic is a function of two variables already, r and r prime, right? R and r prime is already a function of two variables. So when I do that scanning, I'm adding up all the sources, I have to use a third variable, right? So that's the summation in R double prime. Is that clear?
Now we have to take the integral and find the gamma.
Okay.
Now we have to just take the integral
Correct.
and
So if I complete this integral, I'm good.
as a delta function, so it's easy.
It's a delta function, but it's a derivative of a delta function. Good, very good. Since it's a derivative of a delta function, I will be a little careful. Right, basically, whenever it's a derivative of a delta function, it's a derivative of the Green's functions that come. Right, so I had to integrate by parts and
The function, derivative of the
or the derivative of it. If you know how to evaluate a derivative of a delta function, that's good enough. Right, there are two, so you have to, when you put it back, it comes out. Okay. Good.
So del square plus omega square dou c square is like operator, right?
Yes.
So you operate it on Green function, then it gives you the point charge delta function, right?
Stop it again.
Like
Yeah.
that part is operator, right?
This one.
Yeah,
Yes, that's a differential operator.
yeah, then we have that equation. So in order to figure out, you operate that operate on Green function, right?
That operator on the Green's function gives you delta.
That's why we integrate our real function with Green's function included, right? To get the like that.
Or you can think of it like this. Yeah, that is correct. That is symbolic. But if you want, you can think of it like this. G of z comma z prime is equal to delta of z minus z prime, right? That's minus. I can multiply by h of Z prime on both sides. Correct? So put this in, but this comes in because this is a Z operator, so that's H of Z prime. And that's H of Z prime. Right. And if I now put this and then integrate it also, so now what is happening is the d by dz square plus k square integral of dz prime. This is an algebraic pair, and this is H of Z, right? So this is the solution to for F of Z. Correct. So that's your F of Z. So that's more algebraic. The other way, the way you're thinking is more symbolic. Since this is operating on it, this must be the case, but this is more concrete in a sense. But same thing. Okay. Okay, if that's the case, then as Aryan said, you have these. If you want to evaluate that delta function, derivative of a delta function can be evaluated. Remember, so you have dz f of z delta function of delta of z minus z prime is equal to derivative of z prime of f of z prime with a negative sign. That's how a derivative operator of a delta function works. So basically, make it operate on z and put in a negative sign. Here there are two derivatives, so negative sign goes away. So effectively, this is nothing but L plus 1 omega square over c square operating on now. It's very nice because still we are in the same electric potential due to a point charge, right? If you know the electric potential due to a point charge, you know the Green's static with all the modes available. It's just we have to take care of this operator on that, and that works out well. Okay. So the total solution will be know what Green's static is, or Green's function is. There may be a small notation. This I call Green's function. In your notes, you can see that's a Green's function, and this is a Green dyadic, right? Green's dyadic. That's a small notation. Yes.
I have to say that's supposed to be G naught.
This is G naught, yes.
That's wondering if something did.
Yeah, good point. Very bad. I think I'm trying to hurry. That's 20 minutes.
Yeah.
Sorry. I think I'm preoccupied with that deadline. Okay, with me. Okay. From this point, remember we are in the far field approximation, right? Far field approximation. Was basically you take r minus r prime, and that's approximately equal to anyone?
R minus R dot prime.
Very
R
good.
hat.
R minus r hat dot with r prime. That's basically what this whole makes things simple, is that approximation. And in that approximation, we also did that all the derivative operators. What this implies, I should say, this is not an additional additional approximation, this also implies, right? All the derivative operators is basically a switch, right? That's not equal. You replace all the derivative operators with omega over c times r hat. And that's it. This was done during, I think somewhere in the frequency domain when we were working. That makes it nice. Put it in here, be static. Or r prime omega is equal to I coming 2 times. That's your minus, so there's a I square, right? I square makes it minus, so it's minus of omega square over c square comes out. And that is an r hat, and plus, I suppose. Oh.
But I think it should be minus.
Better. Times. Am I missing anything? No. And I have to do this approximation too, right? So I have to approximate that to r minus r hat after the r prime. And 4 pi, in the denominator, you just make it r. Rewrite this in a certain form. We can write this as exponential minus omega square over c square is nothing but k square, but let me keep writing that. So k is omega over c, wave number. So that's e raised to I k r over 4 pi. Let me write the 4 pi. And 1 over 4 pi. 1 minus r hat is nothing but cross product, cross of a cross product. So it is r hat crossed with r hat crossed with 1. Again, we have seen this elsewhere, and that is a 1 over 4 pi. The second piece, I write it separately. I say this is now, just for writing purposes, I introduce a new variable, k prime, where k prime is nothing but a short form for omega over c times r hat. That's your homework basically. All this is the last step in your homework somehow. Right? That's your Green's data in the far field of approximation. If I know that, I basically go all the way back in here. And if I know this is my equation, that's what I'm looking for. That's my Green's data. I can invert this, right? This becomes my source, exactly like what I said, f, g, and z. If I integrate this out, I get back my solution. That here's the strategy. Okay. So, any questions under here?
Why don't we define k instead of k prime?
Oh, because this is going to be associated with r prime.
But k is in direction of r.
A k will be in the incident. Give me a minute. I'm going to use k elsewhere.
Okay.
Okay. Give me a minute. Yeah. Or how about this? Yeah. So there is an incident beam that is going in here. This will be my direction for k. Basically z, right? This is my incident beam. There is a scattering that is happening in this direction. That's r hat, and that's my k prime. So initially there is a K, after scattering, whatever is happening is K prime. Right? Initially there is a wave coming in, after reflection or after scattering, it goes in a certain direction, that's my R prime. And if I want to add up all the solid angle, then I'll add up on K prime, so that's the relation. Okay. So electric field R omega will be equal to, I'm going to leave some space here.
Like, why when we substitute for 4 pi, the absolute value of R minus R dash, when we substitute the approximation to the denominator, it
Why
becomes
did I not write that?
only R? Yeah.
This is the same thing we have been doing all through. So what happens is that if you have f of
It's because the higher terms we
higher terms, so when you take the denominator to the higher, it's the higher order. Right?
Yeah.
It's a higher order. So it's a consistent thing we have been doing. So I just
Yeah.
So if you want the far field approximation is this in the numerator, only this in the denominator, and this everywhere that they're getting out, right? So that's all one after the other. Mainly it is just this.
Okay.
But this is leading to other learning experience. Okay. Any other questions? So that's your Green's function. Now I'm going to invert this equation basically for the source. Now I know the source. I just have to put it together. So, but I'm going to leave some space here. Right? So that's going to, so that's a plus here. B cube R prime. Gamma naught. R comma R prime. Omega. And my source, which is omega square. No, there's no omega square over C square because when I look at it in this terms, this should be on the other side. There's also already this omega square over C square that has been taken care of in the so that is like chi. If this was an isotropic, this will be dyadic. If you want for a moment, let me write it, but this is isotropic in our construction. R prime omega and electric field R prime omega. Okay. Now, whenever I have an inhomogeneous differential equation, that's my source, that's my Green's function. It's also possible that even in the absence of a source, I might have a solution. Right? That's what goes in here. And that's your incident beam. Usually we don't have any solution in the absence of a source, but scattering is a special problem where even in the absence of a source, we have an electric field. If you remove the source, that is an electric field, but that electric field is spectral in the sense on the right hand side it is zero. The incident electric field satisfies the homogeneous differential equation. The incident electric field satisfies a homogeneous differential equation because it's independent of the source. Right? That's the difference between incident electric field and a scattered electric field. So it is independent of the source, and that always can be added. So this is EF R omega, because when I take the whole, if I were to operate this with gamma naught inverse, which is a differential operator, on this is going to be zero, right? So I can always add the homogeneous part to a particular solution. If you have studied partial, if you remember your partial differential equation, there is a particular solution. A particular solution is always off by a homogeneous solution. You can always add that to that, and accordingly your boundary conditions will change. Okay, so that's the idea we have used here. And there is this complication here that the solution has the solution in it. Right? It's not a very convenient thing when you have a solution itself in this. So there is some symbolic structure in there that If the solution is there, it's like a fractal, right?
Like recursive.
Recursive, but it's a recursive, and that's the word. Now you can use recursion. Right? So it's recursive, that means use this in here. Right? So this will become En. Use the recursion. Plus d cube r prime. Yeah, enough. R comma r prime omega divided with chi of r prime omega use recursive and r prime omega plus higher terms. Right, there will be a second term which will have two Green's function now. If I drop this, that's called Rayleigh scatter. That's the easiest thing you can do. Okay, when you drop all the, if it is a high energy scattering you're doing, you cannot drop this. You have to keep all the other ones. So let's say you drop this, right? So if you drop this, it's called Rayleigh scatter. When is that allowed? If wavelength of the incident beam, incident is large compared to the size of scatter. Right? The sky is blue. Why is that?
Rayleigh scatter.
Rayleigh scattering, right?
Like, it's
That's reasonable.
water,
Good answer, right?
But blue's wavelength.
Yeah, you can say there's an omega square that comes up, blue dominates. That's good, okay? But if that is the case, why are the clouds white? Why are the clouds not blue?
like,
Sometimes.
all-
Huh? Water,
Those are black.
huh? Water is blue though. So the
of
idea
this
is,
limit,
huh?
because of this limit.
There is this limit. Cloud, the size of the scatterers are large. Right? This limit doesn't work, and in the high limit, then that blue doesn't dominate anymore. Okay, so so the idea is, I mean, an experiment that you can think of. I never done this. I don't think, or maybe in YouTube, I might be there. Look it up. Is that take a solution of water and start putting in something, and that let's say there are small tiny molecules where there is scattering happening, and it will show up blue, like that water should be blue. And somehow, if you were to crystallize it, like if those small molecules start aggregating, as the size of those molecules get bigger and bigger, it should start becoming white. That blue water should become white. I think that is the reason why ocean, whenever there's a turbulent water, air bubbles start forming in. That's why it is white. Like on the seashore, the water is whitish. Like every time the wave comes in, it's white. I think that's a reason, but there is a lot more to it than just like this might be a dominant effect. I think that's the best way to say it. This is one of the effects. But when it comes to the color of water, there's so many things that are happening. So
Like cold water is mostly because of chlorine, I think, that it's blue. Blue water specifically.
but I say that cool water, even if you don't put in chlorine, it will
The
look blue.
surface is always blue usually.
Yeah.
Yeah, why is that? I say it is,
No, the surface of the pool, not the water.
oh, you mean, no, even if you color it pink,
Yeah, and then.
it will come out blue.
Mm.
And it's not the reflection of the sky. It is a water molecule itself reflecting. That's what I would say. But recently I was talking to the chemistry professor, Puneet Colley, Professor Colley. He's, and even on internet it is full. Like the idea is that water molecules itself have vibration frequencies which dominate on the blue side. And the question is, if you see glacier, they are all, have you guys seen a glacier? Like it's harder to see it when you're in the tropical regions. They're not white. If you really, if you get a chance to look at the glacier, they're
yeah,
bluish.
especially if you like, cross inside there. It's
Exactly.
blue.
Exactly, it's turquoise blue, that's what they say. In fact, even the flowing water, like it's pretty nice, even when it's turbulent, like when I saw it, it was turbulent and still there was this greenish tinge to it. I don't know what's the reason for that, and these are the arguments given that this is probably not Rayleigh scattering. So the argument is that water being blue is probably not Rayleigh scattering. That's the argument. I gave this project to an undergraduate student this semester, and we were hoping to do much, but we didn't make too much progress. But we had a lot of discussion. Another reason why you could say, or one of the arguments that you could say it is water is blue, is that if you were to look at our planet from the space, let's say moon, it apparently looks blue, like you've seen pictures of it, right? It looks blue. And if you look at that picture, it is more blue where there is ocean. So, and wherever there is land, that has atmosphere, remember. Right, so, but that's not blue. So whatever is the cause of blue color of our planet is primarily the water, and it's not the atmospheric scattering. So you can rule that out, because then land also should have been blue otherwise. Right, so these are the arguments, at least some of the input you can take, all this has to be satisfied. So let's stick to the point that Rayleigh scattering apparently is the major component in the sky being blue, a dominant contribution, but let's not immediately conclude that water is blue because of that. Probably there's a good chance that it has surely a component to that. Okay, if that's the case, I have 3 minutes remaining. So now that's what it is. Incident beam, let's say, is a monochromatic wave. And this has an electric field amplitude, that's E. That's just a vector. And if it's a monochromatic wave, mostly this is I, K dotted with R. That's fine. K that I'm introducing, that I was telling earlier, that this is K there. So that's yeah. So that's an incident direction. Since it's an R prime, let me say this is R prime, and that's my R prime. So my electric field is equal to the incident. That I'll keep it as it is. It is basically this. But now here it is R prime, right? So most of this piece comes out. So I have a minus of R hat crossed with R hat crossed with 1, which is going to see only the E naught. That's my E naught coming in. This is how the scattering, you can even see the polarization of the scattering, because this decides how what's the direction of the scatterer would. So we have the polarizations inbuilt in here in this construct. That's here, and there is an e raised to IKR over R. Again, K is just the incident frequency. This has been taken care of. There's an omega square over C square dominates. So this is, that means omega is large for blue, right? Blue dominates over red. That's what it means, and it's a square. And if you square the intensity is square of that, that's 4 times the frequency. So that's taken care of, and I have a 4 pi there. So 1 over 4 pi. And the Q R prime. And what I have remaining is exponential of minus A prime. And there is also this K prime, and I have also a K there, right? So this is K R prime. And chi, which we said is isotropic R prime omega.
What is the integral limit here? Is it just for the source?
Just for the source, the integral means where the source is, where is my chi? I'm collecting all my chi, superposition of chi's. We say superposition of charges when we are doing simple statics. In scattering, superposition of all polarizable materials. Like all molecules that are scattered. Like if this is a sky, I have to collect all my air molecules where there is a chi there. Right, that's what. And each one is contributing this. Like the, in a sense, Green's function for this. No, Green's function where the 1 over R, right? There's a 1 over R. That's your Green's function. Yeah. Yes.
Is there supposed to be a prime? It's the R prime and E dimension.
No, not here, because incident is R, right? And inside the integral, it became R prime.
Okay, so not about.
So here it is R,
Yeah.
right? This is okay. Reasonable?
Yeah.
Now this has a special interpretation. What is this? A function, exponential of something, integrate. Fourier transform, right? So you solve the problem completely. You have a compact expression in the Rayleigh scattering. That's why Rayleigh scattering is so nice that it is a simplified version, but it's an exact solution. Not and exponential of IKR over R omega squared over C squared 1 over 4 pi times Fourier transform now evaluated at K prime minus K omega. So if you know the Fourier transform of the polarizability, you know scattering, and this piece alone here is called the scattering amplitude. This is called the F of theta and phi. That's called the scattering amplitude.
And chi is vector here.
Phi is a dyadic in general, but I assumed somewhere that it is isotropic, so I made it 1. Right, so it is isotropic. If it was not isotropic, the only price is that E naught has to sit on the other side. Right, because this will hit chi, chi will hit E naught. So here, so there is a compact, so I just want to simplify that. That's the only reason why I made it. Otherwise, it goes through nice, very nice. Okay. And remember, intensity, power per unit solid angle is square of the electric field or square of the magnetic field, and that leads to the idea of square of the scattering, and that's why it's called the scattering amplitude. So square that to get that. If you give me 3 more minutes, let me do a one specific problem. What you would do is, you will say that there is a disk. The material here is a disk which has this property, right? You will be given chi. Put that for a disk, do this integral for a disk, like think of a charge density which is on a disk, then you will do the integral on a disk, correct? All the contributions. Same idea here, instead of a charge density, you're saying it is it's a polarizability or susceptibility that is contributing. If it was a point charge, this whole thing will come out, right? Immediately. So let me do this for a point source. So let's say, so this is a point atom. So if there was just a point atom, one atom that is scattering in the sky. Yes, Navika? Us? No?
No.
Okay. So for a point atom, chi of R omega, this is before Fourier transform, is equal to 4 pi alpha. For an atom, you talk about polarizability, and that's your alpha is a constant, times this exists only at a delta function, right? Only at one point in space. That's the position of the atom. Position of atom. Right. Only at the position of the atom, this contributes, it's zero everywhere else. In that case, this is straightforward, f of theta phi is immediate. F of theta phi is basically this integral, right? So it is omega square over c square, that is a 1 over 4 pi. But then there is a 4 pi alpha. And that integral is basically r prime, maybe I should say r prime here, right? So that would be better. Say this is r prime. That will help. So basically replace r prime with s. So I replace r prime with s, it's exponential minus I k prime minus k dotted with s. That's the contribution due to a single atom, like scattering amplitude due to a single atom in the sky. This is the phase that contributes to the scattering. If I square this, what happens to this? This doesn't contribute. So you would think that that is useless. Correct, for a single atom, it's useless. But now let's say there are two atoms. Right? When there are two atoms, there are two pieces in here. When you square it, this goes to 1, the other one goes to 1, the cross term can contribute. That's interference. Okay? So you have to be careful with that, and that can contribute. So that's, and this is how you will begin if you were to do crystallography. This is where you begin from. One atom contributes this one, and crystallography is all about getting collections from here. If you have multiple atoms that are radiating, then how do you add this up? That's what crystallography is. But we'll stop here. You will do this for a disk. That's will be your final exam problem. That you will do that for a disk. And thank you for allowing me 10 more minutes. Thank you for listening in general.
How do you get for point atom 4 pi alpha?
This is an, I'm saying if it was this, consider an atom. For an atom, there is some constant, like a charge, right? The charge density for an atom is Q times the delta function, correct? So chi for an atom is some constant, if I say alpha, times delta function. The polarizability of an atom is alpha. That's just a definition. Okay. Sorry for hurrying and. Okay. Enjoy. Good luck. Don't stress too much for the exams. There's only one question that wouldn't so much time. Just come unprepared.
And it will be Friday 8, yeah.
Yeah, Friday 8, shall we have it here or should we have it in the conference room? Last time where did we have the midterm 1?
Yeah.
Here, okay, so we'll have it. I think we had 7 of the thing. Good.
What if
8.
what if we have it at where we had our potluck?
We can, I don't mind. Is the weather going to be good?
Well, it depends on the weather.
Yeah.
If it's windy, then whatever.
Does anyone have an exam after that? After Friday? Like after Friday, after this exam? So I can get you something to snack on. Is sugar good for you guys are all young, right? Donut is good.
I still go to.
Huh? Chocolate donut. Okay. So, yeah. Okay, chocolate donut. Very good donuts here, by the way.
Dunkin' or Larry's has a cakes.
Larry's cake, where is that?
That's,
Right next to IG.
you know where?
Yeah, is that open still? Are you sure?
Yeah,
Pretty
yeah.
sure, right?
Yeah.
I haven't been there in a while, but.
Yeah, 8 o'clock it will be open, or 7:30
No,
has to be open.
6 p.m. 6 p.m.
Okay,
Or
now
we
I
can-
can get it in the evening, right? Is fresh, no, fresh donuts are good.
Yeah.
There is a discount after 3 p.m.
I'll get the normal, Dunkin' Donuts, is that okay? No
Yeah.
coffee, you have to get the coffee from the student lunch, if you come 5 minutes. I remember to get this, so I had to come 1 hour before for it.
Or we can also go out for dinner after the exam.
Yeah, we can do
Or
that.
dinner
Lunch,
at,
lunch, you mean?
Doesn't matter, lunch or dinner.
You guys want to do that? Yeah, we can do that.
there's a Korean food truck here that I really like.
Okay, so let's go to
Yeah,
the
we
Korean
can try.
food truck for lunch afterwards.
It's by the Walgreens on Wall Street.
Oh, that is a problem though. I have an exam right after this, so 10:15 to 12:15. Can we do it after 12:15? 12:30 we go for lunch?
Yeah.
Does it complicate it? You guys are traveling,
Yeah, the week.
so it's okay to. Yeah, I mean, that's my problem, that if I tell anything, you cannot say no, because you'll be afraid that I'll fail you guys. Or offending me. Yeah, I'll cover the lunch. Okay. Okay, so we go to the Korean food truck. I never been there. So where is the food?
It's, do you know the Walgreens on Wall Street?
Oh, yes, I know the Walgreens.
It's literally parked right next to it. And they're very nice people and, I've been there a lot. It has some pretty good.
So
reviews.
is there a place to sit for a while, like,
There isn't really nowhere to sit though, I guess.
so,
It's just a food truck, I guess.
yeah.
But I mean, if the weather is nice, then we can all just like,
Can
get
we
the
take
food.
it and?
yeah, we're gonna take it and go somewhere, honestly.
And then we go to Bucky's. store?
Yeah, exactly, we can do that,
Okay,
and then just chill there.
so you guys can go, oh, but if you guys go, then I won't be able to pay. Yeah, so we'll all go and get the food and then come back. It will be half an hour.
Yeah, I mean, we can, I'm sure we can pay for us.
Yeah.
This time.
We're adults.
We can pay.
No, then it won't be, I think, then, yeah, I can cover it. I don't get paid too much, but I don't have, I have too much responsibilities.
Go right now.
I don't have kids. But you might have a future kids. The same problem. Yeah, let me go. At 12:30, I'll begin, and then we can go at 1 o'clock. We'll have a late lunch. Is that okay?